Okay, so let's get started. Welcome to week 6 of interactive live sessions for the course on fundamentals of convective heat transfer. It's being offered by NPTEL and instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I'm a PhD scholar at IIT Madras, and like every other week, we shall be solving some problems together. So let's dive into problem number 1, which has got three statements, and then it's asking us to pick which one or more than one statements of them are correct. So read these statements carefully and try to figure out which ones are correct. And then there are some combinations given in the four options below. You can pick the one that matches your answer. So these statements are as follows: that for Prandtl number comparable to 1, both the velocity and thermal boundary layers develop at almost the same rate. Then statement 2 is for Prandtl number much less than 1, the temperature boundary layer will develop at a slower rate than the velocity profile. And statement 3 says that for Prandtl number much greater than 1, the temperature boundary layer or the thermal boundary layer will develop more rapidly than the hydrodynamic boundary layer or the velocity profile. So pick out which of these statements are correct, and then there are some options given below, which is option A says that only statements 1 and 2 are correct. Option B says only statement 1 is correct. Option C says only statement 3 is correct. And option D says that all of them, that is, all the statements 1, 2, and 3 are correct. So Prandtl number, as we know, is the ratio of the momentum diffusivity or the viscosity to the thermal diffusivity, that is alpha. So if let's say the momentum diffusivity is much greater than alpha, then Prandtl number will be much greater than 1. And in that case, you can imagine that the uh, hydrodynamic boundary layer will grow at a much faster rate than the thermal boundary layer. So this corresponds to our option or statement 3, and as it turns out, the statement is false because it says that the thermal boundary layer will develop more rapidly. So statement 3 is incorrect. Now, similarly, along similar lines, so if gamma is if nu is much less than alpha, which means that Prandtl number is much less than 1, in that case, the thermal boundary layer will grow more rapidly than the hydrodynamic boundary layer. But once again, the statement contradicts the truth, saying that the thermal boundary layer will develop at a slower rate. So statement 2 is false as well. Whereas statement 1 is the only correct one, because if Prandtl number is comparable to 1, that means that both the thermal diffusivity as well as the momentum diffusivity are of the same order. In that case, the boundary layers will also develop at almost the same rate. So statement 1 is correct. So you should have picked option B, that is statement 1 is correct. Let's look at the right solution, and it is indeed option B. Okay, so moving on, we'll move on to question number 2, which is asking us for the Nusselt number when there is a uniform wall temperature condition. So, and for a circular pipe, so there are a few important bits of information here, and all of them are important. So it is a circular pipe like this of some radius r naught. Let's say some radius r naught. And the flow is hydrodynamically as well as thermally fully developed. So I'm assuming we will have a velocity profile like this, which is parabolic, which we can solve for, this type of a flow is also known as a Hagen quasi flow. And the thermal boundary layer is also fully developed. So if I, let's say, plot P, which is, uh, non-dimensional form of temperature, which can be written as TW minus T, sorry, TW minus T divided by some T val minus TC. And also, and so since it is fully developed, so this dou phi dou x is equal to 0. This is the thermal profile or temperature profile. And on top of that, we know that it's a uniform wall temperature condition. So this T wall is constant. So in that case, what should be the Nusselt number? That is the main question. So there are four options given below. Option A 3.614, option B 4.021, option C 3.66, or is it option D 4.36? And Nusselt number here will be based on the radius. So, sorry, based on the diameter. So if this is R, then it is actually Nusselt number based on 2 R naught. Okay, so let's take a look at the solution quickly. It's option C, 3.66. So if you go through the derivation as shown in the lectures, you'll get down to this value. What is more important to note is that, for the uniform wall temperature condition, this number is lower. And in the other case that we saw, that is for a uniform heat flux condition, that value would be higher. So that's one of the main things we will keep in mind. And we will move along to question number 3, which is asking us. So once again, there are some important conditions to be taken into account. So the question it says that the axial heat conduction in axial heat conduction. So this is, the heat flux in the x direction in a thermally fully developed laminar slug flow. So now slug flow means that the u is neither a function of x nor a function of y. The u is a constant, which I can say is some um. So I'll write it this way. So u as a function of x or y is simply equal to a constant, that is u of m, um. And I had, sorry. Right. And through parallel plate channels. So I have two parallel plates now, which is separated by a distance to capital H. These are the parallel plates. There is a uniform flow through it, or a slug flow equal to um. And it is thermally fully developed as well. So in that case, uh, and also it is told that it's a uniform wall heat flux condition. So in at any location, Q wall is a constant. So in that case, what happens to the axial heat conduction or axial heat transport, let's say, not just conduction. So is it equal to 1? Is it equal to 0? Does it vary linearly in the axial direction, or does it vary logarithmically in the axial direction? So we'll quickly take a look at the answer. It's 0. Now, how do we get there? So the heat transport in the x direction is simply, dou x of k into dou t dou x. And when the heat the heat flux through the wall is constant, we can write this uh, dou t dou x as simply dc dtc dx, where this is the, or sorry, dtm dtx, where that is the bulk mean temperature as a function of r is simply equal to the Q wall, that is the heat flux from the wall into perimeter, divided by m dot, that is the mass flow rate, into Cp, that is the specific heat. Now, since this is a constant, whatever is in here will also be a constant. So this will be dou dou x of some constant. I will write that down, but that is inconsequential as everything inside it is simply a constant. So the derivative of it will become 0. And that's why it should be option B, that is 0. Okay, so moving on, we'll move on to question number 4 now, which is now asking us that for a uniform heat flux condition, once again, the value of Nusselt number for a thermally fully developed laminar slug flow through parallel plate channel is what? Now, this was one of the simpler cases which we learned initially. So we have two parallel plates separated by a distance 2h, and there is a uniform slug flow through it given by um, and there is a uniform heat flux condition as well. So q dot wall is equal to constant. In this case, what should be the Nusselt number? Should it be option A 8, option B 12, option C 3.66, or option D 4.36? Let's take a look at the solution. It's actually option B 12. It's one of the highest values that we saw. So this was 12, and that for a circular pipe with laminar slug flow and uniform heat flux condition, it was option A 8. Whereas the more realistic values, in case when the flow gets developed, the values get reduced. Now, the reason behind that is that in case of a slug flow, very near the wall also, we have a very high velocity. So that carries away a lot of heat away from the wall. So that is the reason why the theoretical Nusselt number is pretty high, because Nusselt number again depends on, HL by K. This H would be very high in these cases where we are considering slug flow, right? Okay. So moving on, we'll move on to question number 5, which is asking us that in case of uniform wall heat flux condition with respect to uniform wall temperature condition, the increase in heat transfer for hydrodynamically and thermally fully developed flow through circular pipe is how much? Is it option A 16, 18, 17, or 19? So let's say I have two conditions. One is uniform wall heat flux. Let's call it Nusselt number 2. And since we are uh, considering it with respect to uniform wall temperature condition, let's call it Nusselt number 1. So the number we are asking for is the difference, the percentage increase. So Nusselt number 2 minus Nusselt number 1 by Nusselt number 1 into 100%. This is the number that we are looking at. Now, for that, the other informations given are that it's a circular pipe, as well as the flow is hydrodynamically developed, and it's thermally fully developed as well. So in those cases, what are the values of the Nusselt numbers? We saw earlier that for uniform heat flux condition, this is 4.36, and for the uniform wall temperature condition, it's a bit lower, 3.66. So that's why we are getting an increase. So now just plugging in the numbers, 4.36 minus 3.66 divided by 3.66 into 100%, I should get a number. Let me check. So 4.36 minus 3.66 gives me zero point 0.7 into 100 divided by 3.66%. So it's like 70 by 3.66%. Calculate that. 70 divided by 3.66. That is close to 19. That is equal to 19.12 something. We'll just approximate this as 19%. So option D should be correct. And it is indeed correct. Right. So moving on, we'll move on to question number 6 now, which is asking us that once again we have a circular pipe with thermally and hydrodynamically fully developed flow through it with constant properties and uniform wall temperature condition. What happens to the wall heat flux? The wall heat flux varies linearly in the axial direction. Is this statement true or is it false? That's the question. So we know that in case where the uniform wall temperature uh, where we have uniform wall temperature condition with fully developed flow through a circular pipe, we get that mm, the temperature uh, at any location is equal to some T wall, which is a function of x. And this is, I'm writing down the center line temperature, Tx. So we saw that Tc is a function of x, which is equal to T wall as a function of x, minus some exponential to the power some constant into x. Right. So this constant I don't remember right now. You can go and look up in the lectures, but this is the functional form of the temperature profile. Now, the wall heat flux, this is equal to some H into T wall minus Tc, right? So this will be equal to now H into now this difference. This difference is again, okay, some C1 and C2 was there. So this will be now C1 e power, sorry, e power minus C2 into x. Now this varies this actually decays exponentially. So if we just plot it, so I have one constant wall temperature, TW. Okay, so this is not a function of x. Sorry. Hmm. And this temperature, there was some difference here, and it decays exponentially like this. This is the center line temperature. So you can see that this difference, which was very large, actually decreases exponentially. And this temperature difference decreasing exponentially means that the wall heat flux also varies exponentially, not linearly. This mathematical form represents exponential decay. So this was x and this was temperature. So what can we say? We can say that this statement is false because it says that it varies linearly with the axial direction, which is not true. So it's false. I hope things are clear. We'll keep moving on. We'll move on to question number 7 now, which is again a true or false type of question where a statement is given that says that the temperature slope for uniform wall temperature at the wall is lower than the temperature slope for uniform wall heat flux. So we have two cases. Now, whether it's a circular pipe or a parallel plate, nothing is mentioned. So we can take either case because it should hold true for both. Now, in one case, I have the wall temperature, let's call this 1. So in this case, I have constant wall temperature. And in another case, case 2, we have uniform wall heat flux. So in both cases, what happens to the temperature slope? That's the question. Which one is lower, which one is higher? So if we drew the uh, temperature profile for uh, constant temperature, constant wall temperature condition, we will get a temperature profile that somewhat resembles like this. And in this case, we will get a temperature profile something like this. So if we now take a closer look at the slope of temperature near the wall, because that determines what will be the actual heat loss or the rate of convective heat transfer as well as the Nusselt number. Now, that slope in this case you can see is much flatter than this line. This is much sharper. So that means that this statement is true. That is, for the first case, the temperature slope is actually lower than the second case. Let's take a look at the solution. It is indeed true. And that is the reason. So I hope that's clear. Now, we will keep moving on. We'll move on to question number 8 of today's session, which is asking us that for a hydrodynamically and thermally developed flow through a parallel plate channel, the decrease in heat transfer in case of uniform wall temperature in comparison to uniform heat flux is how much? So it's similar to one of the problems that we did earlier, only in this case we have a parallel plate channel and our two cases are these. So in comparison to this, so we'll call this one and call this one two. So what is the percentage change over there? So in this case, the uniform for the uniform wall temperature condition, this is equal to 7.54, and the other one, that is in Nusselt number 1 for uniform heat flux, that is 8.24. Now we will take a look at the percentage decrease in this. So NU2 is lower than NU1. So we are looking at NU1 minus NU2 divided by NU1 or percentage decrease. So it should be with respect to NU2, which is the higher value, into 100%. So let's just plug these numbers in. So we have 8.24 minus 7.54 divided by 8.24 into 100%. So if I just use these numbers, give me a second. 8.24 minus 7.54 is again zero point 0.7. So this boils down to 70 by 8.24. I'm assuming a number close to 9. Let's take a look. So 70 divided by 8.24. Yeah, somewhat 8.5%. That would be the answer. All right, so moving on. Okay, so that was the last question of today's session. We will just, summarize all the cases that we have seen. So we have seen cases with parallel plates and circular pipes, as well as with constant heat flux condition and constant wall temperature condition. And we saw two different flow cases as well, where we had slug flow plus fully developed thermal boundary layer, or we had another case where both the hydrodynamic boundary layer and the thermal boundary layer were fully developed. So in the case where the wall heat flux is constant, then for parallel plates with slug flow, the Nusselt number is 12. For circular pipe, it is 8. So pretty high values. These are, theoretically very high values. And these will be true only for a very small portion of the pipe where, the Prandtl number, first of all, is very low, so the thermal boundary layer develops quickly, but the hydrodynamic boundary layer does not really develop as much. So it would be applicable for that very small region given by, the entrance lengths. Now, another case where, for the rest of the pipe, when there is development of both the boundary layers, in that case, and with heat flux constant, wall heat flux constant, we get the Nusselt numbers for parallel plate as 8.24 and that for circular pipe as 4.36. The actual fractions are these 140 by 17 and 48 by 11. These come from exact solutions of the energy conservation equation. And in the other case where we take the wall temperature to be constant, then we get for parallel plates uh, Nusselt number as 7.54, and for circular pipe we get a smaller number of 4.36. And these are all with both the boundary layers fully developed. Okay, so that's all. Thank you.